Today we introduce orthogonal complements. This is where inner products start splitting spaces cleanly, instead of letting vectors loiter everywhere. Given a subspace U, its orthogonal complement is the collection of all vectors orthogonal to every vector in U. Formally, U perp is the set of vectors x in V such that x is orthogonal to every U in U. This is always a subspace, not just a random pile of perpendicular objects, despite the universe's usual standards. If x and y are orthogonal to U, then any linear combination of x and y is still orthogonal to U. Closure. Obtained without drama for once. In the plane, let U be the horizontal axis. Then U perp is the vertical axis. Every vertical vector is orthogonal to every horizontal vector. Yes, the example is obvious. That is the mercy before the theorem. A vector x splits into a part in U and a part in U perp. The theorem says this clean splitting always happens in finite-dimensional inner product spaces. The symbol direct sum means every vector has exactly one such decomposition. Existence and uniqueness, because apparently one miracle was not enough. Here is the central theorem. Every subspace U comes with an orthogonal partner U perp, and together they split all of V. To prove a direct sum, first show every vector can be written as a sum of two pieces. Then show the overlap of those two subspaces is only the zero vector. No hidden duplicate decompositions allowed. Bureaucracy, but useful. Choose an orthonormal basis of U. Then use it to subtract the U part from any vector x. The vector U is built from the coordinates of x along the orthonormal basis of U, so U is inside U. The leftover vector W is x minus that U part. Now we check that W is orthogonal to U. So every x will be written as a U part plus a perpendicular leftover. If the next calculation works. Mathematical suspense. Tragically legal. It is enough to test W against each basis vector EI, because those basis vectors span U. Orthonormality makes all terms vanish except the ith1. That one cancels the first term. So the result is 0. Thus W lies in U perp and x has the required decomposition. If a vector z lies in both U and U perp, then it is orthogonal to itself. That forces z to be 0. The intersection is trivial. Existence came from subtracting the U part. Uniqueness came from the trivial intersection. The direct sum theorem is done. The next basic result says that if U is a subspace, then taking the orthogonal complement twice gets U back. One inclusion is immediate. Every vector in U is orthogonal to everything in U perp, so it lies in the double complement. For the reverse inclusion, decompose x as U plus W using the direct sum theorem. The W piece lies in both U perp and its complement, so W must be 0. So every vector in the double complement was already in U. Taking perp twice returns the original subspace. Not a suspicious counterfeit. Orthogonal complements collect every vector perpendicular to a subspace. They split the entire space into a piece inside U and a piece perpendicular to U. and taking the orthogonal complement twice returns U itself. Next time, we turn this decomposition into an operator. Orthogonal projection. Finally, a projection that is not just a vague PowerPoint metaphor.